Yeah, so I think an important concept that we learned about fluidized bed was something called minimum fluidization velocity, right? Right? Minimum fluidization velocity. Um, so I was just trying to explain it based on a typical experiment that everyone performs, okay? In which what you do is you basically monitor how does the bed height change as a function of the superficial velocity. In a similar experiment, I can also follow how does the pressure drop change as a function of superficial velocity, right? And we said that in the initial region, right, with the increase in the flow rate, there is a increase in the pressure drop, okay, because of which there's a linear change in the or linear increase in the pressure drop. However, during that period, your bed height remains constant because the upward force that the fluid is basically imparting onto the bed of solids is not enough to lift the particles that form the bed, right? And we said there's a small change in the bed height. That's when all the particles kind of loosen up. There's a small change in the epsilon, okay. However, your pressure drop still continues to remain constant, okay, and that's what we had done, okay. We had done this for people typically do it for a cycle of a cycle, wherein you start with a packed bed, you go on increasing the flow rate, and then you come back to the original state, right? And actually Praveen had asked a question as to why do we take the point B, right? There's this particular line, that's what corresponds to the minimum fluidization velocity, right? And there's a question as to why that is the case, okay. It has to be that point and it should not be this point, okay. That's because of the fact that so when you make a packed bed, okay. Okay, so when you make a packed bed, what do you think these lines, right, the initial line, what do you think it will depend on? So in the initial line is kind of varying in this way, right? That's your initial increase, right? So why doesn't it vary? Why isn't the slope a little steeper or a little smaller? What does that depend on? It depends on the way you pack things in the packed bed, right? It depends on the porosity that you create by packing, okay. And it is known that I can actually create a packed bed of different porosity starting with the same column particle combination, okay. That means if I take a vertical column, if I pour solids, okay, they pack in a particular way and they give rise to a bed of particular epsilon. Now if I do exactly the same process, but in the end if I shake it up, okay, they pack a little differently, right? So that initial line basically depends on the kind of operation that you're trying to do in order to create the packed bed, okay. However, when you do the reverse cycle, okay, when you do the reverse cycle, what you do is you take it to a fluidized state and then you slowly reduce the flow rate, okay. When you do that, okay, the kind of packing factor or the porosity that you achieve is fairly kind of, no matter what kind of solids that you work with. If I take spherical particles, it turns out that this the porosity that you get when you decrease the flow rate is typically around the same value, okay. And that's the reason why people choose the 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 second cycle, okay, where you decrease the flow rate, okay, and that B, okay, where you start seeing the flat line which corresponds to the packed height, right? That's the point where you should be choosing for the minimum fluidization velocity, okay. And it's not this point, because this the superficial velocity corresponding to this point depends on the way you pack stuff, okay. But however, the return cycle, okay, typically always gives you a bed of a porosity which is very similar for whether I use smaller particles, larger particles. As long as I work with the same particle shape, okay, you'll always end up with epsilon m, that is the porosity at the minimum fluidization, which is very close to we discussed in the last class, right? The typical value of 0.36, okay. That's the, okay. And what we had also done was yeah, we said that when you do you basically do force balance, right? You do a force balance wherein you equate the upward force that the fluid is imparting to the bed, okay, when that equals to the weight of the bed, okay, that's when the packed bed starts fluidizing, right? And by equating the pressure force to the weight of the bed, we obtained expression for what is called as a minimum fluidization velocity. And for different conditions, right, when the Reynolds number is less than 1 and when the Reynolds number is greater than 1, okay, and then from that we also calculated what is a typical ratio, okay, what is a typical ratio of the terminal velocity in the particular flow regime again, okay, divided by the minimum fluidization velocity. It turns out that's of the order of 50 for spherical particle for the laminar flow conditions, okay. However, if you take the higher Reynolds number case, that is the turbulent flow conditions, this number basically gives rise to 7.7, right? These are typical values that that is obtained by assuming a particular value of epsilon m, that is the porosity at minimum fluidization, okay. The take home from this particular analysis was that you get a larger range of flow rates over which I can operate the bed under in the fluidized condition, so that the entrainment doesn't happen, right? That means so we said that for you to have the particles continue to remain in the column, I would have to maintain some velocity, right, of the fluid velocity. If the fluid velocity is much larger, okay, or higher than the terminal velocity, what will happen is it will take out all the particles also along with the fluid, right? And we said that is something called as a entrainment, right? When some of the particles from in the bed are carried along with the fluid, that's called an entrainment, and you don't want entrainment to occur, okay. Of course there are cases where entrainment may be required, right? If you really want to say that I have particles of different sizes, I would like to take out the larger ones or smaller ones, right? I can also exploit entrainment in some cases, but however, if you have cases where I don't want the particles to come along with the fluid, okay, then this so basically what I can do is I can actually work with a flow rate range, okay, all the way from whatever value that you're using up to about 50 times the minimum fluidization velocity without entrainment occurring in the case of low Reynolds number case or the laminar flow conditions. However, if you look at the high Reynolds number case, that range of flow rate that I can operate is limited, right? So that's where we are stopped, okay, with the fluidization, right? So any questions that you have about these concepts? If you have any questions, we can discuss. Otherwise, we'll move on to the next topic. Okay. Okay. Next, I want to talk a little bit about some variation of flow through packed beds, but something called as a filtration. Okay. So I mean, the simple definition is that the filtration is the process of removal of solids from a fluid, and this fluid could be either a liquid or a gas, okay. And for you to separate out the solids, you would have to pass this through a filter medium, right? There should be some or this filter medium is also what is called as a septum, okay. That means you have some medium that has the capability of retaining solids, okay. What you do is you have a fluid that contains particles, and you would have to pass it through this medium, and ultimately the particles get deposited on the medium and the clear fluid comes out, right? That's what is done in filtration. And the valuable product of filtration, okay, it could be just the solid particle that you want to recover, or it could be the fluid, it could be both, or it could be neither, okay. It depends on what kind of operation that you're trying to deal with. Can you think of an example where both the fluid and the solids after the filtration are not useful? Can you think of an operation where I'm carrying out filtration using a fluid which contains particles, where After the filtration, I get the solids and the liquid, but none of these products are useful. Yeah. Wastewater treatment, I would call it, I would kind of classify it under cases where the fluid is useful but the solids are not, right? Because if you have a wastewater treatment, right, you have solids, typically the solids are the ones that you want to remove out and throw it out, right? And I would like to use the fluid that comes out, right, the fresh water or the clean water for some use, right? So that will essentially come into this case, right, where the valuable product is a fluid but the solid is not, right? Of course you may have cases where, like say industry has a waste, okay, and if this is a waste sludge, okay, where neither the liquid nor the solid is useful to them, they want to dump it into some some they want to use kind of do some of the how should I say this, some of the after treatment methods, okay. But if that after treatment method requires removal of both the liquid waste and the solid waste, and they may have a separate process for each of them to kind of dispose, right? So when you're doing that, neither the solid nor the fluid is useful, right? In the end they just want to dispose it off, but however they don't want to dispose it as a fluid particle combination, but they want to separate it out because there are certain after treatment methods which are specifically suited for solids, some after treatment method which is specifically suited for the liquid, right? Can you think of an example where the solids are the useful product? What is that? Salt water. But I don't think you can take salt water and then filter it, right? The salt is too small, in size to be retained on a, right? So typically there are a lot of people who work with this nano technology, right? The nanoparticle synthesis of particles and stuff like that, right? Where what people do is they make particles and then they want to take out these particles for some application, right? And typically when they make these particles, it is of course there are several different techniques available for making it, but one of the simple technique that people use is a kind of a chemical synthesis route in which you have the formation of particles in the solution, okay. Now if I want to take out particles from the solution, what is done is typically you can use a centrifugal filtration or or some kind of a process where you retain the solids, okay, and the solids are the useful product, and then the liquid is it could be waste, of course. You may also have cases where if there are some reagents in the liquids, I may I may be wanting to reuse it as well, okay. But however if the particles that you generated are useful, then that's a case where the solids are the useful product and the liquid is not so much, right? Can you think of an example where both are valuable products? Crude oil. What about crude oil? I don't think people use filtration in crude oil. Yeah, maybe during their extraction probably, but not. Okay, so you could have a case where, so imagine a case where I have a particulate dispersion, and say that these particles are kind of acting as a site for some reaction, okay, and say that there's the reaction going from A to B, okay, and it happens on the surface of the particle that are dispersed in the fluid, right? Now of course the reaction products, if they are formed in solution, I can take out the solution and I can use it for I can separate out the product, right? Okay, so therefore the fluid or the liquid, okay, is useful. And you can also, what you can do is after the reaction has happened, I can recycle the particles, right? I can take it out, I can use it back in some next subsequent operations, okay. So essentially what I'm trying to say is that whenever you are working with filtration, right, you can have any combination, okay. You can have a case where only the solid is useful or the fluid is useful. You could have a case where either neither of them are useful, or case where both of them are useful. Okay, it depends on the kind of filtration process that you're going to work with, okay, or the kind of the fluid particle system that you're dealing with. Okay, I have a question here. Okay, think of an example for filtration operation where the suspending fluid is a gas. Yeah. Yeah, that's true, right? So one of the example is, so he's talking about an example where you have a polluted air, and I would like to remove, for example, when people use this mask, right? You would have seen, these days in a traffic junction or somewhere, a lot of people use these masks, right? And the purpose of those masks is essentially to filter out all the solid particles and then let the clean air, right? So you can inhale the clean air, right? So of course, the vehicular emissions. Okay, so there's a like say a diesel engine or a petrol engine, the combustion occurs. Okay, and typically whatever comes out of the engine will have some gases, for example, or some particulate matter. And before the gases, the exhaust is kind of let into the atmosphere, there will be some filters where you basically remove some particulate matter. Okay, that's a case where you may have, that's an example where the filtration operation is carried out to remove the suspended the suspending medium is a fluid, and what you're removing is a particle. Can you think of an example where the suspending particles are liquid and the fluid medium is gas? Can you think of an example where I would like to recover the liquid particles, or the liquid droplets present in a fluid stream, and the fluid is a gas? Again, industrial exhaust, right? For example, you will have cases where the flue gases that come out of the industry, right, can have some mist, right, some liquid droplets, and you would like to recover them. Okay, so essentially filtration is a very important operation, right, in industry. And again, all of you are exposed to filtration when you in daily life as well, right? When people make coffee or tea, right, what you're essentially removing is, when you strain it, right, you have a filter medium, that's your filter medium, and then what you pour onto the filter medium is your coffee plus some coffee particles and milk and everything, right? And what comes out of it is a clear liquid, right, or the coffee, which is the useful product in that case, and you basically dispose your solids, right? Okay, so that's some brief about filtration. I just want to spend a little bit of time talking about classification of filters. Okay, um, and whenever somebody carries out a filtration operation, um, typically the fluid flow through the filter medium occurs because of the pressure difference that you maintain. Okay, we know that for any fluid flow to occur, you need a pressure difference, right? Similarly, in the filtration as well, okay, because you would like to have the fluid flow happening across the filter medium, I would have to maintain a pressure difference across the filter medium, right? And so therefore you can talk about what is called the upstream, okay, and a downstream, right? And that's your filter medium, okay. And of course the solids get deposited on the filter medium, right? So depending upon uh, uh, so there are cases where what you do is you maintain in the upstream, you maintain a pressure which is greater than the atmospheric pressure, and your downstream is maintained at the atmospheric pressure. So this is an example of what is called as a pressure filtration. Okay, this is an example of what is called as a pressure filtration, where the upstream is maintained at a pressure above the atmospheric pressure, and your downstream is the atmospheric pressure. Or you can have a case where your upstream is maintained at atmospheric pressure, however at the downstream you apply a vacuum. Okay, in both cases you're essentially you're applying a pressure difference, and the flow of liquid through the filter medium occurs because of this pressure differential. Okay, and of course there are different ways of maintaining the applying a pressure. For example, okay, there are cases where I can use a pump or a blower, okay, or a centrifugal force, okay, or I can also have a case where where I have a filter medium and I have a long column of liquid above it, right? So there are different ways by which I can apply a pressure greater than that atmospheric pressure. Okay, so it depends on so therefore in terms of the pressure differential across the filter medium, you can classify the filters into two categories. Okay, one is the pressure filters, other one is what is called as a vacuum filters. Okay, and yeah, so you can also classify uh, filters based on what is called as a filtration mechanism. Okay, in what is called as a cake filters, cake filters are typically used when you're trying to filter out a large amount of solids from a slurry. Okay, I have a slurry which contains a large concentration of particles in a fluid. Okay, and what you do is there's a filter medium. Okay, and then that's your upstream, that's your downstream. Okay, and of course all the particles are kind of deposited on the filter medium. Okay, um, now when it comes to clarifying filters, so clarifying filters are typically used when you are required to remove a very small amount of solids. Okay, typically the input to such filters is almost a clear liquid with very few fine particles. Okay, and if your objective is to remove even those small little amount of solid that are present, so you basically pass it through a clarifying filter. And one distinction that you see between the image on the top and the bottom is that most of the solids are kind of deposited over the filter medium in the cake filters, right? That's what the schematic shows. Okay, however, if you look at the clarifying filter, there are a lot of solids that are deposited within the pores, right? That's the pores that are that's the pores of the filter medium. You see that the size of the particles are even smaller than the pores in the filter medium, right? And typically the removal actually occurs because of the addition of these small particles to the surface of the filter medium. Okay, and the only distinction between these two, the cake filters and the clarifying filters, is that one is typically used for cases where you want to remove a large concentration of solids. The second one is used for cases where the concentration of solids in the slurry is very, very small. And the other difference is that the pore size, okay, the size of the pores in the case of cake filters is smaller, mostly smaller than the size of the particles. However, in the case of the clarifying filters, the size of the pores is larger than the particle size that you have, and typically the particles adhere to the surface of the medium because of some some specific interaction between the particles and the medium that you're using. Okay, in what is called as a cross flow filters, what you do is you have a cross stream of suspension, okay, that is being flown over a filter medium. That's the filter medium, right? That's a filter medium. Okay, and there's a suspension which comes from the left, okay, in this case. Okay, and typically what you do is you maintain a specific velocity with which the suspension is basically sent, and the velocity should be sufficiently larger so that the particles do not sediment, right? Okay, because you would like to keep them floating over the filter medium. And what happens, some of the liquid basically comes through the pores that are present in the filter medium, and what you end up to the right is a concentrated dispersion. Okay, so therefore cross flow filters are typically used when you want to convert a slurry from a dilute slurry into a concentrated slurry. Okay, so of course you can do it by other methods. I can take a dispersion which contains a smaller concentration of particles, I can evaporate the liquid, right, and I can make it into a concentrated solution, of course. However, that is much more time consuming, right? Even if I take, like, say, a 10 microliter fluid, it takes about several minutes to dry, right? Therefore, if you want to go from a dilute slurry to a concentrated slurry, it may take much larger time if you want to use something like drying process. However, if you use this cross flow filters, it's a much quicker operation, and I can actually go from a dilute slurry into a concentrated slurry a reasonably quick time. Okay, so therefore, based on the filtration mechanism, you can classify the filters into cake filters, clarifying filters and cross flow filters. Okay, any questions that you have? Okay, so yeah, there's some write-ups, you can go through it later. Okay, now, so I just want to introduce a couple of so the filter media, right? So I said people use septum, or a filter medium for separation of particles, right? And of course, the filter medium or the membrane that you're using for filtration, that should have several requirements, right? So therefore, one of the requirement is that it must retain the solids to be filtered, giving a reasonably clear filtrate, right? So therefore, so the septum that you're using, you should not let the solid particles also along with the fluid, right? The objective is to filter out the solids. Therefore, the filtrate that you get, okay, the filtrate is the fluid that comes in the downstream, right? You have the upstream, the slurry comes in, and whatever comes in the downstream is called a filtrate, right? Okay, therefore, this one of the requirement of the filter medium is that it should retain most of the solids, okay, and it should give a reasonably clear filtrate. It must not plug or blind. Okay, what it basically means is that I have a filter medium, okay, with time, okay, with time what could happen is depending upon the operation that you're trying to deal with, these solid particles may get embedded in the filter medium, right? Of course, that depends on several factors. That depends on the type of the particle that you're working with. It depends on the pressure difference and things like that. Okay, and the moment you have solid particles that kind of are incorporated into the filter medium, that's what is called a plugging, okay, or a blinding, okay, of the medium. And of course, that should not happen. Okay, and of course, it should be chemically resistant. Okay, it should be strong physically as well to withstand whatever operation condition that you are dealing with. Right? You may be doing filtration at high temperature with higher pressure differential. Okay, so you should be able to withstand all these operating conditions. The other requirement is it should permit the cake formed to be discharged cleanly and completely. Okay, so what you do is once the filtration is done, the solids are deposited on the filter medium, right? There should be some easy way of discharging the solids. Okay, and of course it should not be expensive. Okay, so that's some of the requirements of filter medium. The other definition that I want to touch upon is what is called the filter aids. Okay, and as the name itself says, this is something that helps in the filtration process, right? So this is okay, what typically happens is that if the solid particles that are there in the slurry that you are trying to filter, okay, if the particles are too small, okay, and if the particles are what are called slimy, okay, or sticky, okay, then what will happen is during the course of filtration, so what will happen is that the cake that is formed on the filter medium, it becomes very dense. Okay, when it becomes very dense, the porosity is much lower. If the porosity is lower, it's difficult for the filtrate to come out. Okay, therefore ultimately what will happen is the liquid may not even come out. Okay, so what do? I want to avoid that. Okay, what people do is they add some additives. Okay, so these additives they're inert. Okay, they don't do any other job, right? Okay, they don't chemically interact with the liquid, neither the solid, right? They're inert particles, and the moment you add them, what will happen is they will try to maintain a typical porosity throughout the filtration process. Okay, it will prevent the formation of this dense impermeable cakes. Okay, therefore the filtration can continue for a longer period of time. People typically use some cellulose particles. You can you can buy cellulose particles in the market, so I can put it, it's inert. It doesn't really affect either the fluid or the particle, right? And then some silica. Okay, so basically what you do is before you do filtration, you add these additives into the slurry, okay, and carry out filtration. Okay, therefore the cake that is formed has both the solids as well as these additives, okay, and it will help you to maintain a typical porosity that is required for the filtration to occur. Okay, so that's by adding. Okay, so when you add things additionally, okay, into the slurry, okay, that's one way of doing it. The other way of doing it, what is called as a pre-coating. What you do is, so you have a filter medium, I apply some layer, okay, some material on the top of the surface, right, of the filter medium, and it will kind of prevent deposition of fine particles on the surface and things like that. Okay, so either I can use the filter aids or I can use pre-coat. Okay, these are two different ways of ensuring that the filtration occurs smoothly during the course of the operation that you're trying to do. Okay, any questions? Any questions so far? Okay, so then we'll just move on to the next few minutes. I'm going to talk a little bit about so the objective of the remaining class, is to look at principle of cake filtration. So basically, we would like to work, we would like to develop a working equation for filtration. Okay, that's the whole purpose, right? So in essence, I can think of filtration as a special case of flow through packed bed, right? Can I say that filtration is just a special case of flow through packed bed, but the only thing is, in the conventional packed beds, the resistance to flow remains constant, right? But however, in the case of filtration, the resistance to flow, it changes during the course of your operation, right? That's the only difference. Okay, so therefore, what we're going to do is, basically we're going to start with the working equation for flow through packed bed, and we're going to modify it to suit filtration process. Okay, that's what we're going to do. Okay, so in filtration, the flow resistance increases with time as the filter medium becomes clogged, okay, or the filter cake builds up, okay, on the filter medium, right? So therefore, so what we're going to do is, we're going to start with the Ergens equation, which we developed for pressure drop across the packed bed for the flow of a fluid through a packed bed, right? And then we're going to modify that to suit the filtration process. Okay. Now, before we do that, I just have a question, right? So, whenever you're doing filtration process, what do you think are the easily measurable quantities that change during the course of filtration? So I'm carrying out a filtration operation, right? And I would like to measure some parameters during this process. Okay, can you think of, okay, first thing is, can we think of some quantities that we can measure during this process? Okay, the second question is quantities that can be easily measured. Okay, what's your answer? What is that? We can measure the solid as connected, right? So if I have what I can do is, I have a clean filter medium to begin with, okay, and there's a deposition of solids during the process, okay, and I can actually measure it, right? That's, of course, I can do that. Any other parameter? What's that? Porosity. How do we measure porosity during the filtration process? So even the measuring the solids that are deposited on the surface, right, it's a little tough to do. Okay, of course you can put in some sensor and then see, but the quantity that you can easily measure are the flow rate and the pressure drop. Right, I have a filter medium, okay, upstream and the downstream. I can collect the rate at which the filtrate is coming out, right? I can actually monitor that as a function of time, right? That's one quantity that I can measure. And the other quantity that I can measure is the pressure drop that I have applied, or if there's any change during the process, I can also measure what is the pressure drop that is across the bed, right? Okay, so therefore, people talk about two different types of filtration processes, okay, when because of the fact that the quantity that I can measure are the flow rate of the filtrate and the pressure drop. I can talk about what is called as a constant pressure filtration, okay, and what is called as a constant rate filtration, okay. In the constant rate filtration, what is typically done is I am actually collecting the filtrate, right. Of course, if I look at a conventional filtration operation, the flow rate should actually decrease, right, with time, right. That will also, that's what actually also happens in the coffee straining as well, right. I made a coffee and I'm just trying to filter it. Of course, after you know after you pour out small amount of coffee, okay, later on it becomes difficult for the liquid to come out, right. That's because of the cake formation. Now what you do is, if you want to maintain the constant rate of filtration, what you do is you start playing with the pressure drop. Therefore, what you do in a constant rate filtration is, because your objective is to maintain the constant rate of filtration, you go on increasing the pressure drop during the process, so that the filter rate continues to come at the constant rate, but at the expense of progressively increasing the pressure drop across the filter medium. Okay, that's what is called as a constant rate filtration. In the case of constant pressure filtration, what you do is you fix the pressure drop, right. I have an upstream pressure and a downstream pressure. I fix that, okay. I maintain that constant during the course of filtration, and I let the pressure let the flow rate fall, okay. Typically, when people work with this cake filtration, okay, which involves passing of a slurry over a filter medium and collecting of the filtrate at the downstream, people typically work with either the constant pressure filtration mode or a constant rate filtration mode, and we are going to develop working equations for both of them, okay. Right. So the other thing that is also important is that, so in the case of so that's a schematic that you have, right. So this is your okay, that's your the cake filtration, a schematic. Upstream, the medium, there's a cake formation, and that's downstream, right. Now if you look at this, if you want to think about the pressure drop, right, now there's two contribution to the pressure drop, right. One pressure drop that comes because of the cake that is formed on the filter medium. The other pressure drop comes because of the medium itself, right, because medium is also a porous medium, right. The medium that you're using for filtration, it's of course again another porous medium, okay. There's when the liquid flows through the porous medium, there's of course a pressure drop that corresponds to the flow through the medium itself, that is this part, and delta Pc that corresponds to the pressure drop across the cake. Therefore, the total pressure drop for the filtration process is the pressure drop across the cake plus the pressure drop across the medium, right. And of course, that the pressure drop across the medium is 0 to begin with, okay, and it may remain constant throughout the process if the medium is mechanically robust, there is no blinding, right. When okay, if the medium is not modified in any way during the course of filtration, your delta Pm is going to continue to remain constant throughout the filtration process. But however, if there is a blinding, okay, or if there is a higher pressure difference across the medium, even delta Pm could also change, okay. However, delta Pc would always be there, and it could increase during the course of filtration depending upon how much of filter cake is deposited on the filter medium, right. So we'll think a little bit about some of these things and then try and develop a working equation for them in the next class, okay. So I'll stop here, and if you have any questions, I'll be happy to answer. Otherwise, okay, we can stop here. Any questions that you have? Simple concept, right? I mean, filtration is a fairly simple concept, so we'll try and work with the working equations in the next class, okay. And then yeah, so we'll have class on Tuesday and Wednesday, and then a tutorial on the last day, which is Friday, okay. So if you don't want a tutorial, we can also end it by Wednesday. Otherwise, we'll have a last class on Wednesday as well. Thursday, Friday, sorry. Yeah. Okay. Thanks.